Okay, we're going to record this. This is going to have to suffice for both periods 4 and 6 through a small mix-up with the recording from the other class. Oops. So these are the concepts that you've got some homework problems on. They're not going to be on the test, but I want you to have seen them so that they're familiar to you if you're going on in chemistry. What we have been using up to this point is the old ideal gas law, PV equals nRT, and you're all pretty proficient with it, no problems. What I want to ask you about is this piece. So if I gave you 100 grams of nitrogen, and you know the molar mass of nitrogen, it's what, 28.02 grams per mole? Yes? If you solve that problem, whoops, I just gave it away. What would you be finding? N. Yeah. You win a prize. So you'd be finding number of moles. And you've been doing that since chapter 3. This is really pretty basic. So all that this part is the mass of the sample, little m, over the molar mass, big M. Well, what that does is that gives us something that we can actually plug in for N. And we end up with a new version of the ideal gas law that relates pressure, volume, temperature, and the mass of a sample and the molar mass of a gas. So now what we have is PV equals little m over big M RT. Or it's more commonly written as PV equals little m RT over big M. So any of the problems that you've seen in the homework that ask you for molar mass or name a gas so that you can go find the molar mass on a table, this is what you're looking at. Okay, so this is the first sort of variant of the ideal gas law. There's more. So if we rearrange this and we move that V over, so we have P equals M mass of the sample over RT over V times molar mass. There's something else hidden in there. Mass over volume. What is mass per unit volume? Density. How much stuff per unit volume you see. That is what we call density. Yeah, so now we have one more substitution that we can do. And I'm going to do this on the next page for clarity. So we already had PV equals little m RT over big M. Now we have P equals DRT over big M, which I like to say as puddle equals dirt over mud. It works nicely. So we've got the density of a substance, the ideal gas constant, temperature, and molar mass. So we now just have two more formulas that we can use for these kind of problems. And actually numbers 19, 20, 21, 22 are all ideal gas law problems using these two permutations. So with those, you'll be able to do those problems. We'll take a break for 4, come back, and do the next thing. This is the cool stuff. So we kind of already did this on your quiz when you had those last two problems where you had reactions and you had to work out some volumes. Here's the cheater shortcut that you're going to love. If we have any reaction where everything is a gas, so let's do an example such as, what is this called? Combustion of what? Which is? Methane. This is the combustion of methane. You guys are good. So here we have the combustion of methane. Everything in there is a gas. Okay? The methane, the oxygen are gases. The CO2 that's being driven off is a gas. The water that's coming off of this is a gas. There's water vapor. Okay. Everything there is a gas. If I tell you that we combust 75 liters of methane, and I want to know how many liters of water vapor we produce, you're going to love this. You really are going to love this. Whoops. Because the little cheater shortcut is that you can use the coefficients the same way you've used mole ratios as volume ratios. The only condition is that everything that's reacting has to be at the same pressure and temperature. Well, guess what? These things are together. They're reacting together. They're at the same temperature and pressure. So we can just do this. 75 liters of methane. For every 1 liter of methane that reacts, we get 2 liters of water vapor. Oh, we produce 150 liters of water vapor. Couldn't be easier. Isn't that cool? Yeah. Now, when does this not work? If one of those things is not a gas. You know, like combustion of magnesium. If you burn a coil of magnesium, the magnesium metal is not a gas. It's combining with oxygen, which is. So that's where you have to do the things where you do a piece of stoichiometry and then you do ideal gas law or something else like that. So that's really all we have to say. And I'll note here, if you've got a volume for one thing and a mass for something else, you do have to go through moles. That's where you have to do the stoichiometric conversions. And you just have to have the pressure, temperature, all that stuff for everything. So we won't do a whole lot of practice with this. We won't go any further with the gas stoichiometry than what we did on the quiz. I anticipate you'll have like 3 problems, pick 2, something, or on the test. 3 problems, pick 2, something like that. Okay, now, here's the last idea we're going to discuss. Come on. Do you remember what effusion is? Do you remember what diffusion is? What's diffusion? We'll start with diffusion.
Diffusion is where they're just slowly from the air, like if you spray the perfume, how it like slowly disperses.
Okay. So what you're describing is we have an area of, and the diffusion happens in all fluids, so that would be gases and liquids. And we have particles moving from areas of high concentration to areas of low concentration until they're evenly distributed. Okay, that's diffusion. What's effusion? How is it different? Small hole, right. So I will draw my little 2 small holes here. So again, the balance of that movement tends to be from high concentration to low concentration, though things also move back the other direction, but they're really moving until they're at equilibrium. And then they keep moving back and forth, but the rates are the same. So that's effusion and diffusion. Now, all of that aside, and there's a big, long derivation we can do with this, we're not going to. I just want to talk a little bit about my little friend here. Molar mass, 2.02 grams per mole. So I should make that a big M. And my other friend here, mass 32.00 grams per mole. If these 2 things are at the same temperature, remember kinetic energy is a proxy for temperature, so they have the same amount of kinetic energy. If these are at the same temperature, which one of them is going to move faster? Yeah, my little guy. So at the same temp, we have faster, and we have slower. Oops. Okay. Because the thing with the less mass moves faster. Honda Civic full of cotton balls versus a semi-trailer full of cement blocks. Remember that temperature is actually just a proxy for kinetic energy. So we're really just measuring the kinetic energy of a substance. And kinetic energy is 1/2 mv squared. So if they're at the same temp, that means they have the same kinetic energy. Well, that means the lower the mass, the higher the velocity. There's an inverse relationship between mass and velocity. Okay, great. What this means is that we can actually measure and compare rates of diffusion and effusion. So we're not going to do, I'm only going to tell you this, that the rate of, and this is either diffusion or effusion, diffusion of gas A over the rate of diffusion of gas B is equal to the square root of the molar mass of B divided by the square root of the molar mass of A. Okay, it's a pretty simple mathematical relationship. We can make it a little bit more complicated, but we're not going to. I want you to have seen this, though. There are about 3 different ways we can use this. We're going to keep it simple. So let's go back and recall our little friends here. Our little, what is that 2.02? What is it?
2.02.
Yeah, what gas is that? Mass of 2.02? Hydrogen. So we're going to say that hydrogen is gas A, and what would our 32 be? Oxygen. So that's O2. So we're just going to, I mean, this is really about as simple as they come. The rate of A over the rate of B equals then the square root of molar mass of oxygen, 32.00, over the square root of 2.02. So what number do we get? Okay, so we have a raw number here, and we have 4 sig figs, so we could say 3.980. What are our units? This was grams per mole. This was grams per mole. Let's see, grams cancel, moles cancel. What are our units? It's a ratio. No units. Ratios are unitless. That was a trick question. Sorry. Okay, so we've got this comparison of the rates. What does it really mean? What does it really mean? So what it means is that the rate of hydrogen to the rate of oxygen is 3.980 to 1. What it means is that hydrogen moves about 4 times faster than oxygen. So if we were to take a long sort of meter stick kind of apparatus and we were to set a couple of them end to end, I'm going to run out of space. If we have our little tiny hydrogen and our big walloping oxygen, in the time it takes the oxygen to move 1 meter, the hydrogen has gone 4 meters. It's still going. There, change that line color so it's a little bit easier to see. That hydrogen is still going. So in the time it takes oxygen to move 1 meter, hydrogen has moved 3.980 meters. Okay? It's just a comparison of rate. Now, one of the fun little practical applications of this, I used to do this, I don't do it anymore because we had to evacuate the room. So I learned my lesson. They make clear glass tubes with little measurement markings on here. And this is a common, chemistry demo kind of thing. So you take a cotton wad on each end. You soak this one with HCl. You soak this one with ammonia. So hydrochloric acid, hydrochloric acid, and that's ammonia. And then you jam the cotton ball into the end of the tube. Well, this HCl will off-gas chlorine gas molecules. You'll get chlorine gas molecules. The ammonia will actually off-gas ammonium ions in a sort of little cloud. Which one of those will move? Here's the cool part. When they come together, they form a white ring inside the tube. You get a precipitate that comes out. It's ammonium chloride. Which one moves faster? What are their masses? So figure it out. What's chlorine's mass? Well, it's a chlorine molecule. So chlorine's what, about 35 grams per mole? So two of them joined together, what's their approximate mass? 70-ish. What about ammonia? So you've got nitrogen 14.01 plus 4 hydrogens 4.04. So about 18.05. Okay. So which one of them is going to move faster? The ammonia is going to move faster. Yeah, the ammonium ion is going to move much faster. So where do you think the white ring forms? Closer to the HCl or closer to the NH3? The white ring forms over here. So you get this cloud inside the tube right there. Because, let me fix that. In the time that it takes the chlorine to get this far, the ammonium has been able to get that far because it moves faster. It can travel further in the same distance. So it's a neat demo. It's just hard to control the amounts, and like I said, we had to evacuate the classroom, so I'm not doing that again. That's it. Oh, the fumes were terrible. It was bad. It was very bad. So I added number 39 is your practice for this idea. Okay, so that's added to the homework. Homework is still due tomorrow. The other ones are there. Hopefully you're getting them done. And that's it. That's all we got, folks.